So today we have James Fairbanks talking about Julia and category theory.
Yeah, thanks. I'm from the Georgia Tech Research Institute in Atlanta, Georgia. And I'm going to talk today about applied category theory. We've been implementing some stuff in software that is in the Julia language, and I want to talk about it. So there's this thing called model fusion, where you build models of systems, be they physical, chemical, biological, and then you want to take two systems and combine them into a model of the combined system. And that's called model fusion. And a tool that has been developed here, a mathematical tool called decorated Cospans by the organizers of the seminar, is a really good tool for understanding it. And that's kind of the perspective. And I'm going to talk about implementations too. So I think that applied category theory is an opportunity to fundamentally reshape scientific computing. The current pipeline of how math gets implemented on computers to do science goes from domain understanding to math to code to results, going down. And at each step, there's a manual process of like understanding the physics or the biology, and then making a mathematical model, and then writing code that solves that mathematical model. And then you hit code, and like compilers create executables, and then you run those executables and you get answers. But we want to move the automation up that stack so that the human just has to understand the domain and write some math, and then everything else can be automated. And so our approach is so what you need to do is have a language for doing math that computers can understand. And we think that applied category theory is that language. In particular, generalized algebraic theories as implemented in a particular computer algebra system, and then code generation. And we use the language that's best for code generation, which I think is Julia. Cool. And so kind of where we got started here, and why I think this is at all feasible, is that scientific computing is dominated by these modeling frameworks, like MATLAB, Mathematica, Stan, JUMP, TensorFlow, and it's not dominated yet, but I think SemanticModels is going to be there. And so each of these modeling frameworks have some type of math that they specialize in. So MATLAB, it's linear algebra, right? Everything is either multiplying matrices or solving linear systems or computing eigenvectors. And so you can do a lot of science with just AX equals B. Mathematica takes more like broader perspective on algebra, not just linear algebra, but broader perspective, and really is known for kind of encoding a computer algebra of differential calculus, differentiating, integrating, stuff like that. Stan is probabilistic programming, so we can represent stochastic processes in a programming language and then like automate simulation and inference in those stochastic processes. So you describe your data generating process as some Bayesian network type thing, and then Stan can answer these questions for you. Same with JUMP for optimization. And they all have a language in which you write like you specify the things. But they're all ad hoc and tailored for their domain. So the people who wrote Stan didn't think about TensorFlow graphs or Mathematica expressions. They're like mutually incompatible. Oh, that's way more slides than I thought. OK. Yeah, so we want to unify this. And like, what is the language for unifying math? It's category theory. And I kind of think about it this way. So you start in some domain, and you extract out a syntax and a semantics that helps you understand that domain. So the syntax is just, how do I describe phenomena in this scientific area? So a good example of this, like this is the audience most familiar with this type of thing. You have circuit diagrams, and your circuits have terminals, and they have wires between those terminals, and a drawing of a circuit is syntax that encodes that circuit into a data structure. Then you have behavior, semantics, for that circuit, which is a relation on voltages that it imposes on the terminals. So you want to compute, given this circuit, if I put this much current here, how much current and voltage will be everywhere. So that's the semantics. And so the ACT community has done a lot of work on this F, functorial semantics for modeling languages. But then we need to actually compute stuff. And so this whole right-hand side is about computing. I want to take an example of a model described in the syntax, so this circuit diagram, and generate a program with a compiler that when I run that program, I get the voltages out, right? F is functorial, meaning that it preserves the composition and tensor product in the syntax. So whatever combinations you can do in the syntax, you can also do in the semantics, and F preserves those relationships. But when we're over talking about code, I don't want these to be functorial, because functoriality in the code is like, there's a lot already written on this chalkboard. So, and it's category theory. I don't want to erase this good category theory. Yeah. It's monotonically increasing category theory. OK, so in code, I don't want to compose my systems f of g as like the normal definition of this, where f of g of x equals f of g of x, where I run the program that's g, I take the value that it computes, and I run the program that's f. I don't want to do that. What I want to do is combine my systems and then get one program that I run that solves the whole thing. So that's why compile and execute are not functors. And then solvers are embedded in the class of all programs in a programming language. It's the PL, so programming language. Cool. And you know, not all programs are the result of compiling some syntax. There's only a very small class of programs that are that way. Cool. So this is, I said I have stuff implemented in software. And this is an example of how this software works. So you define a signature for monoidal categories that describes the things you can do in a monoidal category. So for example, there are objects. Does this pointer work? Yep. There are objects and HOMs. HOMs have a domain and a codomain, which are objects. So there are relations, not relations, but relationships between the objects. And then you can do, you have some other operations. So you have for every object, there's an identity, which is a HOM from A to A. So the identity on A is a HOM from A to A. If I compose F, which is a HOM from A to B, and G, which is a HOM from B to C, I get a HOM from A to C. That's function composition. I have some Unicode syntax. And that's awesome because Julia is awesome. It lets you write Unicode operators. So that really helps like things look like math, right? Because we're just going to use the math symbol. And then you have this other structure. So this is like the sequential composition of functions. And then O times is the parallel composition. So I can tensor objects and get a new object, or I can tensor morphisms and get a new morphism by like tupling the inputs and tupling the outputs. I know everyone who regularly comes to the ACT seminar knows this, but we have some Julia community people here, so going through it for them. And then you have this special object called the M unit. Cool. And then we have more Unicode. Cool. So when you describe this signature, yeah?
What's this left arrow? At the end of the compose line, you didn't say what that was.
Oh, what this guy is?
Yeah.
It's like where A is an object and B is an object and C is an object.
Oh, I see. Okay, 'cause that was
Yeah. So right, so you could have like repeated the A : ob, B : ob everywhere.
Okay.
Yeah. And so this syntax is based on the Julia syntax for like defining types and functions, and the types of function. So you kind of, when you're doing this part where you axiomatize your domain into a syntax category, you define a signature like this. And that gives you a DSL for describing morphisms in that category. So this is the category of enzyme kinetics, chemistry. So over here is a signature on the left, where you've got objects. So it inherits from monoidal category. So all the stuff from the monoidal category is also here. So for any pair of objects x, y, I have an object called complex. For every object x, I have a degraded form. For every object x, I have an activated form. Then I have reactions like binding, which take an x and a y and create the complex xy. Unbinding, which takes the complex xy and produces an x and a y. And so here the plus is the O times. I've cleaned up this notation here for the slides. So it doesn't exactly match this, which is real code that really works. This code is cleaned up to fit on the slide. But, so yeah, so you have binding, unbinding, degrading, cleaving, activating, activation. And then you have these axioms like cleaving is defined as binding and then degrading. Activation is defined as binding, activating, unbinding. And you have this constraint here, like the thing that you unbind is the activated form of one of the things you bound. So that defines how chemistry works, a very narrow subslice of enzyme chemistry. And then we automatically generate this wiring diagram thing over here where we can describe reactions as programs. And so that reaction that's described in that DSL is like you have an E and an A and they bind, and that gives you an EA complex. And then F happens, and you get a activated E and a P. Then unbinding happens, and you get the EA and the P comes out. And then a B comes over here, it binds to the activated E, you get the EA B complex. G happens, you get EQ, they unbind, you get E and Q. And so you can describe chemical reactions in this DSL. And so I think it's pretty cool that you have a computer algebra system for chemistry, and all it took was kind of writing down the rules of chemistry. There's actually a DSL for generating DSLs. Pretty cool. Yeah?
Are the types of F and G inferred by text?
Yeah, they're actually left out. There was another step here where you wrote down the types of F and G. Okay. Yeah, there's like a free chemistry where you give explicit generators. Yeah. Cool. And so you have kind of, this is the classical notation that would appear in a paper. And this is called a ping pong reaction, kind of because E ping pongs between being activated and unactivated. So it's like a classic enzyme kinetics thing. And so the notation in the chemistry textbook is not specific enough to generate a simulator from. You need something with a little bit more detail. And so kind of generalized algebraic theories tell you what that detail needs to be. And here's the expression in a machine readable, machine understandable form. Yeah?
So when I look at the chemistry diagram, well, when I look at the wiring diagram you generated, it looks like everything is kind of left to right. But in the chemistry equation, there's sort of these double arrows.
Yeah. So in order to capture the left harpoons, you have to have, there's a reverse where you, yeah, there's a, like, F has a dagger that goes backwards, and G does as well. And really in chemistry, everything does. So it's like a self-dual thing. Yeah. So I think kind of benefits of ACT for scientists is that we can structure their scientific knowledge in a much higher level of abstraction, or sorry, structure their knowledge in the level of abstraction they know, as opposed to abstractions like multiply the concentrations and subtract from the constant, like, instead of dealing with numbers, they're dealing with the abstractions of their domain. And then term rewriting on these expressions allows us to optimize the code. We're not optimizing code, we're optimizing problems. And one of the classic things in scientific computing is learn enough about the domain structure to exploit it. And we want to build algorithms that can do that for us, which means we have to encode the domain structure into data somehow. Cool. Benefits of, oh, and then, so we can go fast. That's the part. That's the end goal. Yeah.
So you said data. What do you exactly mean by that? Like, do you mean the DSL?
Yeah. So this,
DSL is data?
the information here in A, like subfigure A, that's the data. You have to encode the knowledge about the science into some data structure for the computer. So that's the data that does that. Cool. Yeah, and the benefits of thinking about science for ACT is that every domain of science is going to be some new type of category with some wrinkle in how the different substructures interact with each other, right? So this like binding and unbinding and reversible processes versus non-reversible processes, and transient phenomena versus steady state phenomena. That all can help us learn new category theory. An example was lenses and learners, or learners and lenses, where like looking at machine learning helped us understand category theory in a deeper way. So getting to model fusion. Oh, cool. For model fusion, this is a thing that scientists do all the time, where they make some model, say, of malaria. So you have people and mosquitoes, and they give each other, the mosquitoes that have malaria will infect the people, and the people who have malaria will infect the mosquitoes when they get bitten. Instead of the people don't bite the mosquitoes. And then there's a logical Volterra dynamics of like wolves eat sheep. And so I want to study the predator-prey dynamics between populations of wolves and sheep. And then say I have some question that's like, if I introduce a new type of bird into an ecosystem, will it increase or decrease the amount of malaria, assuming that those birds eat mosquitoes? So I want to add two models in such a way that I get a sensible model of the combined system. And so the current state-of-the-art technique here is to write two simulators and then share data between those simulators. Like every time I want to know how many birds there are, I need to ask the bird model. And then whenever I need to know how many mosquitoes there are, I need to ask the malaria model. And I do message passing of data in order to couple these simulators. It's inefficient.
Why?
Why?
Why is it inefficient?
Why is it inefficient? It's inefficient from a development effort because the developers have to agree on data interchange formats, and they have to do all this inter-process communication and
No, but if they're just two sets of ODs, you could just couple them, right?
yeah. So so the question was, if they're just two sets of ODs, you just couple them. And so you have to go back to the math step in order to couple the ODEs. You have to unwind you have to go results, unwind to code, unwind to math, and then couple the math, then rewrite the code, and then the compiler takes over, right? So we want to automate that part. In this case, it's it's not that many variables, it's not that much code. You could do it by hand. Substantially bigger projects have been done by hand. But we want it scaling up to now think about systems that have hundreds of variables. And I want to combine them with another system with hundreds of variables, stuff like that. So the models just being ODEs is what I was going to talk about next. So we're going to use Petri net decorated cospans for this, where a Petri net is a bipartite graph where there are circles for vertices and squares for transitions. And so this one is the SIR model of disease progression. So an infected person and a susceptible person combine to create 2 infected people, and then an infected person will spontaneously recover into a recovered person. And they correspond to this differential equation. And so the scientists would much rather think at the level of infection and recovery here in the Petri net than at the level of differential equations. And like you can always just couple the differential equations, but you can already see like there's already more characters over here. There's only 1, 2, 3, 4, 5, 6 characters in the Petri net. It's like more than that over there. And so this is kind of timely. Coronavirus outbreak. Here's a new paper published a couple weeks ago, last week. And they modeled the new coronavirus as an SEIR process, or SEIRD process, which is more complicated because it's got an incubation period called exposed. You can recover and become susceptible again, or not. You know, different diseases have different structures here. And so I wanted to, at this point, go to the chalkboard and write out an example, yeah, I have time, kind of how the whole pipeline works. So you'd start with your model susceptible, exposed, T2 goes to I. It's not exactly what I wrote. Doesn't match what I showed earlier. So if this is your Petri net, sorry, this is your Petri net, like how do you get the differential equations? I wanted to show that it's like totally automatable, and then what the final code looks like. So you go first, for each transition, T3, you're going to have some step where you calculate PSI, V2 is beta 2E, V3 is beta 3I. So for each transition 1, 2, 3, you multiply the in arrows. So T1 takes an S and an I, so it's the product of S and I times some parameter for this transition. And then T2 takes an E, so there's nothing to multiply E by except the parameter. And T3 takes an I, right? And then you get, so these are going to be like, these are some temporary variables we need. And so we get S dot equals negative V1 because I'm taking, kind of every time this transition happens, I take this quantity from it. E dot is V1 minus V2 because every time T1 happens, I get some mass every time this transition happens. But every time this transition happens, I lose some mass because it's an out arrow. Right, so I take transition 1 and I get transition 1. Oh, sorry.
I think they want that down arrow.
Right.
Because you have 2 people coming in and only 1 person going out.
Yeah. So this would be plus V1 minus V3 plus V2. And then R dot is plus V3. Yeah. Cool. And then, so this gives you like, okay, what were the differential equations I was trying to solve for this Petri net. And then you embed this into a Julia code that does writing code on the board using diffeq. U naught equals 100, 1, 0, 0. So I have 100 susceptible people, 1 infected person, 1 exposed person, no infected people, and no recovered people. This is the beginning of the outbreak. My betas are a vector of a half, a third, a fifth. My time domain is 0 to 365. So I create a problem, which is an ODE problem with f this guy is f u naught beta t, and I call solve of p. And so this is the modeling framework in Julia. You declare that you're going to use the modeling framework. You set up initial conditions and parameters in a time domain. And then you declare that to be a problem. You have to pass it a function handle to the function that defines the dynamics as a Julia program. Or sorry, as a Julia function. And then you just call solve on that problem. And when you call solve, you get a solution, which is some time series of data over that time domain. And this is where the compositional structure in the programming language is not what we're trying to preserve. If I compose two systems, I don't take the solution and use that as the initial condition for the next problem, right? Like I can't solve a bigger system by using the solution to the subsystem. I have to manipulate this guy. I mean, I can't just pass the sol object into a ODE problem object.
I think if you're clever, you probably can. Can't you? I mean, that's effectively a function that's like a function of time. So that's going to be a forcing function into your next problem.
But the next problem is happening over the same time domain.
Yeah.
You'll see as we do the composition, you'll see why that isn't quite.
It's like you want to compose the f's, or the arguments, right?
Right. I want to manipulate the f's. I don't want to manipulate the programs. And this is also why we want to automate things. If I change f by adding a new variable to my Petri net, I have to make a bunch of coordinated changes. I have to change the calculations of the fees. I have to change the calculations of the derivatives. I have to change the number of initial conditions. If I add a transition, I have to add a new parameter. I have to pass that parameter into this script. There's a lot of coordinated changes, and that's why it's error prone, and that's why we want to automate it. So why don't you just couple the ODEs? Coupling the ODEs is like distributed changes throughout the code base. Oh, so I had this up. So if you're familiar with hypergraph categories, and if you're not, this might seem a little weird. You have these objects, or these morphisms in a hypergraph category. There's a dot missing in the first one, starting off strong. So the ID, it has one input and one output, and no transitions. The swap, sigma, has 2 inputs, 2 outputs, and the order of the outputs is the opposite of the order of the inputs. The cap has no inputs and 2 outputs. And the cup has 2 inputs and no outputs. Then we have some generators, like F, G, and H, which encode kind of basic building blocks of Petri nets. So F is the infection operation, right? It takes it has 1 input and 1 output. Infects. Sorry, is that right? Yeah, that's right. G is exposure. It has 2 inputs and 2 outputs, and is this guy, like just this part. H is spontaneous. It has 1 input, 1 output, and it's just spontaneous progression. So then we can build up our SEIR model, this one here, by composing those primitive building blocks. So you start out, and it's G times H tensor identity times cup. And that kind of, what does it do? It moves the infected variable. Moves the, oh, sorry, that's what it does. It adds the exposed progresses to infected. This rightmost transition, what I've labeled here as T2. So G times H tensor identity times cup adds this transition. Then to that, we need to move an input to become an output. So we're going to use the cap for that. And then we want to add the spontaneous reaction from infected to recovered. And so that's another H, but it's backwards. So it's the dagger. So the dagger just means all the arrows are backwards.
What do the arrows mean?
Which arrows?
I don't know. The arrow at the bottom right, for example.
So sorry, the arrows inside the Petri net are like this state is consumed by this transition. And then this arrow is this state is produced by this transition. The arrows over here are like this is the first input, and it points to this variable. This is the first output, points to that variable. This has two inputs. The first one is this one. The second one is that one. And these diagrams are, I don't have the Tixie macros that went into the your book. So I had to. So this is Google Draw diagrams. This Tixie is hard. Yeah, cool. So then, like wiring diagrams in this decorated cospan category are recipes for model fusion, where it tells you how. No, still doing good on time. Like how to wire things up to get complex systems out of little systems. And so you have this wiring diagram, and you say, let me attach to each one the Petri net that it's supposed to have. And so kind of this is a birth-death process with predation. And this is a more complicated Lotka-Volterra process where I have rabbits, wolves, and sheep. So I get these big Petri nets. And then for each Petri net, I can get the corresponding differential equations. Here. So here's the malaria example where people are giving malaria to mosquitoes and vice versa. It's kind of, I have susceptible people, infected mosquitoes, and susceptible mosquitoes. And this is where the infected mosquito gives malaria to the susceptible person. This one is the infected person gives malaria to the susceptible mosquito. Infected person, susceptible mosquito. And then both species can be simultaneously cured. Over here. That was close. And so then we get, you like follow this recipe for gluing the Petri nets together, and it gives you this big Petri net. Then you apply this function to differential equations, which gives you the formulas over here. Then you could like simplify those formulas. Yeah.
So where's the scientist involved? Can you show in this model like there?
Where? Yeah.
There?
So they're involved when they pick the generators. Like they say the list of generators. That's like, what does infection mean? What does curing mean? And then they're involved when they write the wiring diagrams. And so then there's a lot going on here. Here's the model fusion where we combine the malaria model with the Lotka-Volterra model to get an example of people and mosquitoes giving each other malaria and birds that eat mosquitoes. And so you get they make this wiring diagram in the top right. Kind of, you see there's like the clip art picture. Scientists make these clip art pictures and they're like, I made a model. and they need like a modeling language that's, they love pictures, right? Like you will pry pictures from their cold dead hands. But they need a formal language in which to draw the pictures that makes sense. And so we think string diagrams is that formal language. So they would write the string diagram there. and they picked the generators. They said for each of these box, for each box, what Petri net does it go with? And so then you can just apply decorated cospans and compose decorated cospans via push out of the spans in the middle. That's this.
And that part's automated.
Yeah. So this thing, right? So I have some x, y, z, and I want to compute. So I have a model from x to y, a model from y to z. I want to compute the composition, which is a model from x to z. And that's totally automated. Software kind of figures out, how do I follow this recipe to glue the model components together? Then the scientist is also important when they tell you, like, this Petri net, how do I turn a Petri net into a differential equation? That, you have to figure that out too.
So, for example, how do you tell it that the bird affects the mosquito but not the human?
Yeah, so in the informal diagram, that's not entirely clear. But in this circuity looking thing, the bird wire never touches a people wire. Like, there's no process that has a bird wire come in and a people wire also come in. So there's no way for the population of birds to affect the population of people. Now they do via, like, the birds eat the mosquitoes and then the mosquitoes interact with the people. But there's no direct coupling.
So how do you identify the wires as being people wires?
So, yeah.
Wires come into a box and then something comes out. So
Oh, when you say the generators, when you're saying the generators, you're like, you can use types on the, you can put types on the circles. And so then you would be able to use like type checking to make sure that if a process expected a bird population and a mosquito population, you couldn't put a people wire in. This is untyped because we're using, it's kind of like the untyped FinSet Cospans, so that we're not leveraging type information. We're just counting how many variables go in and how many variables go out, and all variables are of the same type in this model, but that's a natural generalization.
So when you say a generator, is that like a Petri net primitive?
Yeah.
And you plug this into these boxes?
Yeah. Okay. And so you say you have to say which boxes go with which primitive. Yeah.
And when you specify Petri net, you also need to specify the differential equation.
So,
Particular
yeah, sorry. You have to specify the coefficients of the differential equation in order to run the simulator. Like somebody has to write down the fact that when I have a Petri net and I want the differential equations, I do this. I look at each transition and I multiply the in degree. I multiply the in neighborhood. And then when I want to compute the derivative, I subtract these things and then I add, like somebody had to write that down. Right. So you have to define, like, what does a Petri net mean in terms of differential equations?
The scientist gets the betas, right?
Yeah. So when you compile your Petri net into differential equations, the betas are an argument to the program. So the u, the beta, and the t are arguments to the program. So then the scientist comes in again and is like, okay, well, 100, 1, 0, 0, a half, a third, a fifth, 0 to 365 days. Run it.
except that usually there's only parameters that you don't know.
Yeah. So you have to either pick values or infer them from data. It's been a year, David. We've only worked on this for a year. How long have we been doing scientific modeling?
But that's always the problem in scientific modeling,
Yeah.
right?
Right. So we're only looking at this part where you go from math to code. And then, yeah.
Can you, given an ordinary difficulty function, will semantic models just be able to convert that into a Petri net?
Yeah, so if the difficulty came from a Petri net, and so it has this structure, you can infer which Petri net it came from, up to isomorphism. So yeah, you could do that. And so we have the tools to do that in semantic models, to read out what Petri net does this code implement.
So I could technically write this not going to a model and something else. Just two equations, just tell semantic models to couple them.
Yeah.
If I write them,
Yeah. And they have to be, if you just wrote the differential equations out, there are lots of differential equations for which there is no Petri net, that differential equation is so like usability is an issue, right? So one of the reasons, like, why don't we just have the scientists write Petri nets? Well, the problem with that is, like, there's no abstraction in Petri nets where you can, like, make a big network and then reuse it. There's no reusability, there's no abstraction, there's no higher order functions, stuff like that like programming has, which is why people write programs instead of writing Petri nets directly. So we have a syntax for doing this model fusion where you describe the recipe for fusing the models as a program in a DSL. Then you read that DSL and you get the wiring diagram. And you can convert the wiring diagram into an algebraic expression in a computer algebra system of generalized algebraic theories. And so the thing on the top is easy to write. The thing in the middle is easy to read. And the thing on the bottom is easy for the computer to manipulate. So that's a big part of usability. Right?
To generate these diagrams.
Yeah, so this capability is all provided by Catlab, which if you attended this class 2 weeks ago, Evan Patterson would have, he talked about this. And yeah, so this functionality where you write the wiring diagram as a program just came out of a conversation at the Riverside meeting a couple of weeks ago, where I was like, Evan, it'd be really great if instead of writing these ginormous formulas or building these graphs by hand using add edge, add vertex, add edge, if I could just write the program and we calculate what the wiring diagram is, and we take the wiring diagram and calculate the expression. So yeah. Go ahead.
It's like a linear lambda calculus term or something like that?
Yeah.
Okay.
So it's embedded in Julia,
Yeah.
which is a Lisp. And so metaprogramming is easy. And it's kind of like single static assignment,
Yeah.
where you create wires with equals, creates a new wire. Function calls create boxes. They attach to the wires that are their arguments, and the functions can produce tuples. And then you have these special things like if you reuse a variable name, it introduces a copy operation. So if your category doesn't support copying and you reuse a variable name, it will type error.
Yeah.
Like, this program does not parse because it's not a program that's valid within the DSL defined by your axioms. So copying, merging, deleting, swapping, all that stuff. Yeah.
Is this at all inspired by compiling the category like Malaria, or is it like
Yes. That's definitely an Evan question. But that name is in the... I only can answer that question affirmatively because there are comments in the code that refer to that by name. So I know that that's what Evan was thinking. Or at least I know that that's what Evan wants us to think that he was thinking. Cool. So in order to use this, you have to implement your models as some type in Julia that supports the following operations. Disjoint union, square cup, which takes two models and gives you a model. Quotient, which takes a model and an equivalent relation and gives you a new model. And it does this like variable sharing part. So you say you give it a model, and you say, what variables in this model should be fused into one variable? That's the equivalence relation. And then we we do all the cospan arithmetic to figure out what that equivalence relation is based on the cospans. And that's just like kind of index math. Yeah.
That's the gluing outputs of one piece
Yeah.
of input to another.
Yeah. Yeah, basically the rule for gluing outputs to inputs is if there's a thing in Y that says my input, thing in Y that is representing the output of the first model and also representing an input to the second model. Those two variables are fused into one variable.
Where is that specified
In
in?
category theory. That's like the definition of cospan composition. And so just want to go back to like why we use generalized algebraic theories is it lets you describe these axiomatic systems for representing your models. And it's kind of universal, so GATs are closed under abstraction. So the theory of GATs is a GAT, which is pretty cool. And yeah, so the to-do list, term rewriting, normal forms, usability, stuff like that. And yeah, and then you get to like build these systems that work at the level of abstraction of the scientist. So the scientist can think in terms of their domain concepts and then automatically generate simulators of those models. And so we're trying to capture more types of scientific behavior. So parameter estimation is a thing where you, for example, you'd have like a Petri net, convert that to ODEs, run those ODEs to get time series. And you also have some schema, collect data that fits that schema, and compare the data to the simulation to calculate a loss of how good the parameters are. Then you go and update the parameters. So like, how do we capture that? That's like learning. It's parameter estimation. So can we capture all of the things that scientists do with models as category theoretic operations? And we think that decorated cospans is a good formalism of model fusion. And all these other modeling activities can be formalized as well in terms of ACT. So thank you guys for listening. I'll take questions. David.
So, can you just explain these colored boxes?
Yeah, they're the subsystems. So these boxes correspond to the malaria subsystem, and they're being glued to this mutual predation subsystem, which is being glued to the vital dynamics subsystem. Yeah, and
Everything sort of, I mean, the arrows that are coming out that side.
Yeah.
Come back in somehow.
They don't.
Oh, that's just a.
It's not so like this diagram is not modeling the dynamics of the system. It's modeling the model fusion. It's like it's the recipe for how I glue these things together. It's not modeling like people travel. It's like the variable that represents people is what's traveling along the wire, not like people traveling along the wire. So it's a little wonky, but everything. There's a lot of stuff that can be represented with wiring diagrams, and once you do, it really clarifies your thinking. So just being a tool for thinking, I found Catlab, this whole like make an axiomatization of your thing, draw examples as wiring diagrams, has been a really good tool for thinking about processes.
So I want to understand, I see
Yeah.
three levels of abstraction. The wiring diagram, the Petri nets, and the ODE.
Mhm.
I'm wondering, is the ODE...
And then the date, and then the time series. That's the solution.
Like,
Yeah, fourth level. Yeah.
Like, that's when you run the thing.
Mhm.
So the ODE, is that specified by the scientist? Like I can...
Yeah, so it's specified by kind of one scientist who says, we're going to use Petri nets to model chemistry via differential equations. And he defines that once. And then each chemist comes in, and they don't have to worry about that. They just specify Petri nets.
But in a sense, like you can swap out ODE these for
Stochastic Gillespie algorithms. Yes, so that's the thing I didn't talk about that semantic models does. You can take the same Petri net and generate a stochastic Gillespie simulation that is like for small populations. If I only had 6 people, I need to do a stochastic simulation.
So, and what is the thing with the Petri nets? Is that like hard-coded in your system, or like swapping that level of abstraction
yes.
to something else?
So the Petri nets play the role of one modeling framework, going all the way back to the beginning. So like the Petri nets play the role of one modeling framework where the language, like the math they do is like mass action kinetics. The input specification is this graph, this bipartite graph. And the description is like chemistry. So yeah, they're like one submodule is for reasoning about Petri nets. But the Petri net package, there's like a petri.jl that Micah, who's here, wrote. And it is independent of semantic models from a like code perspective. So it's like a plugin. And so everything is written as if the Petri model package existed first and semantic models was being written later. So the Petri package knows nothing about category theory, which I think is cool. Yeah, Brendan.
That's just thanks for the talk and also for putting this stuff to work. I'm interested in just getting more clarity on the transition from the wiring diagram to the Petri net. So if you could go back to a slide where...
Yeah, so these diagrams are a little inconsistent with how these diagrams are drawn.
So maybe I could just try and describe my understanding and you can tell me. Maybe the next slide is actually slightly better with A and B. Yeah,
okay.
Okay, this works good. So I understand each of the parts of the system. There's already some sort of Petri net building blocks that's specified by the scientist, and they're associated to some of these wiring diagrams, or you can build a wiring diagram out of each of the parts.
Yeah, so
these are the things that were in the colored braces earlier. And then from...
Yeah, so let me just put it this way. Each box in this diagram gets replaced with a Petri net.
Right.
And then fused into a big Petri net.
And the fusion is that when you draw a wire between two separate models, you glue those states together from the underlying Petri nets that you sort of use as generators for these models.
Yeah, okay. But we're not doing the gluing via like handling the wires explicitly. We're doing it via the expression that's like tensor product these things, then compose with this. There's no parentheses here, so this is ambiguous. But I think it's like tensor binds tighter than compose. So you tensor first, and you tensor these, and you tensor these, and this. And then you compose. And so it's just using the composition rule of the Cospans. So it's not like explicitly handling this wire means there's a variable. So building the Petri net from the wiring diagram is functorial.
Assuming you already knew
what the generators were. Assuming you know the generators.
Okay, assuming you know the generators. Okay.
Yeah. Then like this formula is the recipe for the model fusion, not the graph.
Right.
Here.
But the graph generates that expression.
Yeah, using Catlab. Not uniquely, but up to isomorphism.
Yeah.
So in each box is a whole
Petri net.
Petri net, and there are all sorts of dynamics and stuff, and so on every wire is kind of like coming out of a box is kind of a time series in some sense.
Yes.
Right. And then is it just a coincidence of this particular model? So there's lots of feedback inside of a box.
Yeah.
In your picture, there was no feedback between the bracketed pieces. Was that a coincidence?
So it's a coincidence of how we chose the generators. So the way we chose the generators is basically all the variables are all the variables on all the generators are both inputs and outputs. Oh. And that's so that you don't have to think about feedback.
You grouped all the feedback together into the pieces.
Yeah. So it makes it easier to think about how to make this formula if all the inputs are all the outputs just for the generators. then it's easier to think about how to make this formula because you don't have to be like.
The scientist
then
doesn't need to do it that way. You just did it for the slides.
Yeah, I did it because this example predates the parse wiring diagram macro, and so now that that exists, you wouldn't do it this way. You would only use you'd have your generators be like these slides. So these are newer than the other slides. So here now now the inputs and outputs track the Petri net input and output as opposed to just being arbitrary assignments. But yeah, that's because the usability matured. It's now simpler. Yeah.
Okay, maybe we should pause and ask questions afterwards. But
Okay.
thanks again, James.
Thank you, guys.